A resistor is something that if it is very high, like if resistance is very high, like let's say something like 100 kilo ohms, it might even be so overprotective that current might never want to flow inside again. It will just block all the whole current. Resistance is very useful, and that is why you see that if you open, oh sorry, that is why you see that if you open a socket, you see a LED inside. You see a light inside, and be like, but that man said it that time that if you put two 20 volts for a light that needs like let's say 3 volts, will it not go to burn? Why is it not burning? So like the question that Mr. Kaide displayed that time, that each LED they did something like this. They put a resistor there, 200 volts. The light turn on. Another one, they put a resistor there, 12 volts. The light turn on. The light is going to turn on. But if we look closely at that picture, we're going to see that the resistor for the 200 volts was like 100 kilo ohms. The resistor for the 12 volts was like let's say like one, and this let's say like 10 kilo ohms. The reason why the light did not burn very fast is because of two great man in the world of physics, that laws. Let me just discuss a little bit about it, about the laws. And we have Kirchhoff, we have Ohm's law. Now, for that light, let me just do some fast rap on it. For that light itself, a LED is going to, it depends on the color. Color red light is going to take maximum of 1.5 to 1.8 volts for its own operation. That's the maximum light color red light is going to use to on. But when you are supplying, let's say 220, let me approximate it to 2 volts. Let's say you are supplying 220 volts, and that red light you are using is what? 2 volts. How many volts is going to remain? It's going to remain 218 volts. That 218 volt that remains is going to be what is going to be in the what? Resistor. That's going to be in the what? Resistor. The 218 volts is what the resistor is going to hold. Now, why is it not that this 2 volts that is a light is being powered by 220 volts, yet is not burning? Because of this. This law is Kirchhoff voltage law. It's an advanced term, KVL, Kirchhoff voltage law. There's not another man again who discovered resistance, and so his name was Ohms. OHMS, Ohm's law. So his own law was this: current is equals to voltage over resistance. Now let's assume that that resistance is up to what? 100 kilo ohms, that is 100,000. 100,000, and the voltage passing through the resistor itself is 218. Now let's see the current that is going to pass through it. The current is going to pass through this circuit is going to be close to what? 0.000 something 2 amps. So can you see the current? The current is going to be very, very small, that even the light itself may not feel that something is even inside it. That is why those lights inside socket are able to what? Are able to get strong without burning, because of the what? Current passing through them is very small. But if you just connect the light direct to socket, pow, it will blow. If you put 10 kilo ohms resistor there, put it there with the light, it will blow, pow. If you put 100 kilo ohms there, it will even blow also, pow, because of what? The current depth is not enough to allow many electrons to flow. And I said earlier, current is just telling us that this is the amount of the electron flowing. So if you have like this kind of amount of electron flowing, even the light itself is going to be enjoying. I'm going to also demonstrate it, but not with a high voltage. I'm going to use a high resistor to show you how the light is going to turn on. But let us enter inside LED. Now let me rub off this first part, and I can rub off. Okay, let me leave this. We're done with digital multimeter. So now, what is an LED? An LED is also a diode. It's also a diode. I'll go to discuss about diode in another class. This is the symbol of a diode first. This is a diode here. A diode is a very stubborn electron. A stubborn component in electronics. It does not even grip for anything. This sign alone tells us how stubborn it is. It means that if electron is going, that is the end. It can never go back. For it to go back is impossible. So now, what a diode is telling us that a diode allows current to flow was just a direction. If current to flow like this thing I'm going to tell you, no matter how stubborn you are, no matter how stubborn you are, it can never flow back. That is why a diode is being used in converting AC to DC. That is another term. That means no matter how stubborn that alternating current is, once it pass through inside this diode, it can never go back again. But those AC too are very stubborn. That's why we now have a capacitor to make it smooth. But that's another term. Now a diode is a component that is saying that if this is if electricity pass like this, it can never go back. And a diode has what we call biasing. A diode has what we call biasing. But a diode has its own sign. This is the positive of the diode. This place without this stubborn sign. And this is negative of the diode. Positive, negative. Now this is now how a diode is very stubborn. Very, very stubborn. And it's very useful. Let's say you want to use a diode in a circuit now. You now go and connect your negative here. You put your connect your battery here, battery negative to this way. Connect your battery negative to here. Maybe that time your very person was blind. Connected his battery negative to here. He now expected a current to flow here. No, that is what we call reverse biasing. The current can never flow because of the diode only wants you to connect it properly. If you want to use this place, connect the positive of a battery here so that current will go to flow and go to wherever I want to. Or if you want to use here, connect your negative of a battery and so on. So now if you connect it correctly, let's say you put your positive here, your battery positive here. You now connect it like this. That is what we call forward biasing. Forward biasing. Forward. But if you don't connect any power source, any battery or anything to your diode, that is zero biasing. That means you are not connecting anything to it. And the diode does not care. It's resting on its own. So we're discussing more about the diode next week because of we're going to be discussing about the layers of the diode, semiconductor, how the diode actually work, why diode is very stubborn. So now our main thing is now a what? LED, light emitting diode. Now this LED is also a what? It's also a diode. That means it allows current to flow in just one direction. I'm going to be demonstrating it. I'm going to on a light. I'm going to connect it one way, it will on. Turn the other way, it will never on. That is a what? Light emitting diode. Meaning what? LED. That means the diode that its own work is what? It is to give out light, to dash out light. That is why we look at the symbol of the diode, it's something like this. It means that this particular diode you are seeing is what? Giving out light, is giving out a light on its own. That is what we call LED, light emitting diode. Now, let's now discuss about this light emitting diode. If you see most of the light, if you see most of the diode, if you see most of the lights that we use, you see color red, you see color green, you see color blue, you now see color white. But color white, there's a way they did color white. This is what it was, either they combined these three together, but they did something wonderful. Well, the way they did this wonderful was for color white. If you look at the white light, let me show that I have one here. If you look closely at a white light, you see, if you look closely at a white light, you see something that look like something like color yellow there. That thing that look like color yellow. And I said that before they made a white light, it was a combination of blue light and yellow light. But fortunately for us, yellow was red and green. So the thing that gave us was white. But now that time I said something inside the group that out of the whole light, the only one that gave engineers problem was the what? Was the blue light. Why was that? It's now come to something very wonderful in the world of physics. If you look at rainbow color, that time they used to pronounce it Roygbiv. ROYGBIV. Red, orange, yellow, green, blue, indigo, violet. This one, cancel it, you don't need it. This one to cancel it, you don't need it. We only need what? RGB. As way it is arranged like this, the one with the highest wavelength is another term. Highest wavelength. Then followed by this one. Then followed by this one. Lowest. Although it has lowest wavelength, but it now gave us a very big problem in the world of physics. Why? Because of, as it says, light emitting diode, it has to do with some kind of physics stuff that has to do with what band gap and something else. But let me simplify it. What we mean wavelength and this is what we mean. There's a formula in physics. E is equals to HF. And this F, don't just forget about the formula if it's looking troublesome. F is equals to C over lambda, where lambda is, the lambda here is wavelength. Wavelength. So energy, that means the energy to produce each light is now going to give us what? H times, what is our F? C over lambda. C over lambda. So energy is equals to what? HC over lambda. But fortunately for us, no matter the color of the light, whether red, blue, orange, this is constant, this H, Planck constant is constant, this C, speed of light is constant. But it's belong all of us have done physics. So let me just assume this one. If you add something together, it's going to give us what? 50. Let me just assume it's just 50. Now let's now see where the problem is. For red light, the wavelength, this thing that look like upside down Y, the wavelength is very big. Let me say the wavelength was 10 meter. Let me just assume it's 10 meter. Let them now calculate the energy the light is going to use. E is equals to, the sum of these things is going to give us what? 50 over 10. 50 over 10 equals 5 joules. Okay, 5 joules, abi. Let's now see for green. Green, let's say green was 8. So it's going to be what? 50 over 8. Okay, wait, please, I'm coming. Like 8 times 48, 6.25. So let's say 6 joules. Now for blue, the one with the stubborn edge, his own wavelength was very what? Is very low. And let's say the wavelength was 2 meter. Now what's going to happen? What's going to be energy? The energy is going to what? 50 divided by 2. Can you see 25 or 25 joules? Can you now see that this was the main problem why it was difficult for them to what? Produce blue light? Because they're looking for a material that material, before the material can do what? Can emit light, it must use this energy. But the material, there is some of them were using very little energy, very little energy. But for them to produce blue light, they're looking for a material that need a very what? A very high energy. For red light, this 5. For green light, it needs what? 6. For this stubborn guy here, it needs what? 25. So with that, it was now difficult for them to produce it. But after they were able to produce it, it now enabled them to have what? To win a Nobel Prize. No, I'm going to explain it for them. But with the fact that it needs a very high energy, it now needs a what? High voltage to operate. I'm going to be showing the voltage. A red light voltage is around 1.8 volts or less than, maybe less than or equal to 1.8 volts. For green, I don't know the color of green, but for blue, that is the multimeter. In case you want to buy your multimeter, this multimeter is a multimeter that automatically shuts down by itself. Since I'm not using it, it's going to turn off. That is the meaning of the sign. Turn, meaning that it's going to soon turn off. So now for blue light is something like less than or equals to 3.2 volts or 3 volts. Yeah? So it means that if we are turn on the light with a resistor, you're going to see that the red light is going to use like 1.8 volts. Blue light is going to use like 3.2 volts. Yet these blue lights consume a lot of energy. Why? The reason why it's consuming a lot of energy is leading us to the place where we have power is equals to current times voltage. Current times voltage. Because of, for instance, now, if because of in your phone, our phone that we're using every day, that's turn off. In our phone that we're using every day, this red light and blue light that what leads to the what? Pixel. Pixel. That what led to the what? Pixel. And for them to, let's say that green is also part, for them to be able to combine together to make a sharp white color, they must have the same level of what? Brightness. And the only way that can be achieved is by doing what? Giving them same same current. Wait, please. Is by giving them the same current. Let's say that for this circuit, I gave two of them 1 amps. That current was total 1 amps. For the power now, let's calculate this one as 18 more power. For the red light, what is the voltage of the red light? 1.8. What is the current? 1 amps. The power is going to be what? 1.8 times 1, that is what? 1.8 watts. For the blue light, what is the voltage of the stubborn blue light? Blue. We have 3.2. What is the current? 1. So what is the total watts is using? 3.2 watts. That said that blue consume more power than red light. But due to the fact that there is a resistor there, the actual current it might be using might be lesser than 1 amp. So that is it about the blue light and everything. So now with the combination of these red and blue lights, it was now able for us to, and green light, so it was able for us to what, create white light. And as I said earlier, that is why I said that those old alarm clocks, many of them were in color red because at that time the brain were not sharp to produce blue light. Even though the brain has produced blue light, they were not able to, because of power loss, they were not able to do it. So now this is what is going to happen. For us to on a light, we are going to use a resistor. I'm going to draw in a circuit diagram. I'm going to do a light particle now. For us to on a light, let's say we use a resistor. We're not connected to the light. We're not connected to the light. Something like that. I'm going to explain the diagram also. Let's say that this guy over here, this our light is 5 volts. My power bank is 5 volts. This one use, I don't know, sha. This might use like 1.5 volts. The many voltage used by this resistor is going to give us what? Going to be close to 3.5 volts. I'm going to be explaining it. Oh. But before I explain it now, because we're going to be doing a practical now after the whole long talk. So this is it, a breadboard. This is a breadboard here. So let me explain this clearly. This is a breadboard here. So now I'm going to be drawing a circuit diagram for our LED that, or our light that we want to turn on. Because of as an engineer, if you want to build a house, you must first draw your what? Your plan, where your room wants to be, where the kitchen wants to be. It's only people that want to cook food that does not have right plan. They just mix all the whole ingredients together. But as an engineer, you're going to mix it properly. So now let me start. The first thing you must do is since you know your components, write it down. Component 1, resistor. Resistor. You know the symbol. Use the symbol like this. Component 2, why isn't just only 2 components? LED. This is the symbol of a LED. This is the symbol of a LED. Then we now have your jumper wire. So component 3, our battery. Now this is the symbol of a battery, and a battery is a DC. When I mean DC, DC, that means direct current. That means this kind of current flows in one direction. We have AC, we have DC. So now battery DC, this is symbol of, this is what is mostly used for battery symbol. This is a cell. This is a cell. So now in case maybe next time you see something like this in a circuit diagram, so now this place, this short leg means the minus. Why this long leg means the what? Means the plus. That is the meaning of the what? The meaning of those things. This one means the minus, one means the plus. So after that, this is the only thing we need to build our circuit diagram. Now what do you think we now do next? Okay, you be like, okay, everybody know that this is our battery here. Now I'm going to be using 2 markers to show positive and negative. This is our battery here. This is our negative, this is our positive. How do you now connect it to the light? I said earlier that this place is negative of the diode. The one that having this line. while this one is a positive. How do you now connect it? You can have, since it's just a circuit diagram, you can make it look neat. Okay, see this place is representing positive of our light and positive of our battery. How do you now connect? So it just be like, oh, it's very simple. You just take your diode, position it also the same way. Positive, negative. This is a diode. Okay, it's the same thing. But you know that you have looked at it that okay, it's just simple. Just combine them together with your red wire and with your what? With your black wire and your red wire. But know that if you plug this thing under 1 second, the light is going to blow. Why? Because of what? There's no resistor. So now, if you are using a resistor, you can put your resistor in this place or put it in this place. But most especially for me, I used to connect the resistor in this place because of sometimes what you imagine is that current is flowing from here to this place and come to this place. But you can put it anywhere you want. But you are using just only one resistor. You know that you want to on the light, you go and buy two resistor, put one here, put one here. You're just wasting your money. Although it's 15 euro. So now just pick your resistor. This is symbol of a resistor. Put your resistor here and complete the circuit. Don't forget to put your sign. So now we're done with our circuit. This is our circuit. This is the battery, positive, then it's going through this resistor. We're also going to slow it down. Then to enter this the light of our diode. Then to now go again and come back to the battery minus. That is how the thing flow. It go like this, like a circle. Go like this, go like this, and go like that. Now I'm going to try this one. This is the correct one. This is the correct one I'm going to do. But let me now try another wrong one again. I'm going to try 4 diagrams. I'm going to also replace and put the resistor here. I'm going to do this real. So just draw this. This time around, I'm going to put my resistor in the negative. So this. And the next one, I'm going to reverse it. I'm going to reverse the light. Uh, so I'm going to reverse the light. If you can see clearly, I'm reversing it. Let's see whether it's going to on. That show you how stubborn the diode is. If you connect it in reverse bias, that means if you connect it wrongly, you go and put positive in negative, it will never on. So now let us try it out. So let's try that. And also, the first I'm going to do that, I'm going to connect it the right way and the wrong way. And I'm going to also show you why connecting a high resistor could also act like doing over sabi in your circuit. So now let us do this. So now I'm using this circuit. Move aside. So first of all, okay, I'm going to do the whole 3 circuits together. I'm using the 3030 resistor so that our light can be brighter. Because of if you use a lower resistor, we're going to see the light. We're going to see the light also. So if you look closely, if you look closely at the breadboard, I've already used a wire. This is another type of jumper wire. I've connected here as my negative. So now I want to put my resistor. This is the resistor. So I'm going to put it from this place I'm using as my positive to this place here. So insert it properly. You need to fit it. Now if you can look at it, this place is the negative, place is the positive. So current is going to flow and reach this place. So I'm going to take my light. And also in the light, as I said earlier, that the light has a what? Positive and negative. I'm looking for blue. Now if you look at this light properly, you see something. You see that one is shorter, one is longer. This one that is the shortest one is the negative of the light. This one that is the longest is the positive of the light. But some people are just stubborn. If they buy this light, they don't even care whether I put or negative. They will trim the leg to be equal. How they now know is very well. Now there's not that app to use to know it. If you look at it, it might not be clear. But on the because of it's clear and this is I'm seeing it. Let me draw it on the board. If you look at the LED, inside the LED there's something I used to look at. Let's this is how the light is. This is how big the light is. There's something I used to look at inside the LED. Something like this and something like this. Now this is not the thing. This one is connected here. Also connected here. Something like this. Now you can see that this one is very small. Smaller, this one is bigger. Now the smallest one here is the positive. While the biggest one is what? Negative. That's another way. And another way is that if you look closely at the round shape of the this thing, one place is having here as a very one place having here continuously round like this. Why I now just having it to be very sharp. But that one someone might not observe it faster. The two fastest ways, if you look at the pins, the longest one is the positive, shortest one is the negative. But if you look at inside, you can see the inside one very fast also. This one that has this small thing is the negative. This one that has this small thing is the positive, this one is negative. So because of I've been used to it, it is easier for me to identify it faster. So now let me connect it. So let me just use the one I just explained now, the this thing, the long one as the positive. So I'll put it. You can say I can put it anywhere, and I'll try to extend it to reach the negative place. So if you can see it, the positive is in the positive line, while the negative is in the negative line. Now let's turn it on. This is my power source here. I'm connected to my power bank. It is 5 volts. Let me measure it to show you the real 5 volts. So my multimeter is put to the place for measuring voltage. So you do it like this, 5 volts. But if you mistakenly touch the two wires together, that's what they call short circuit. It's going to make the voltage very low and the current will increase. But that is another topic on its own. And this is why the current is increasing is so that no matter what, it want to make the formula of power to be equal. Like now since we have 5 volts, let us power it. So we have our negative here. Though the last time I said it that this whole place is separate from here, but I've already been able to combine two of them together so that any power that is flowing here is going to flow down. So let us and I can keep the position anyway. So can you see light has was turned on. So this is it. The light has turned on already. So now let me now show you that this is I think turned off. The power bank has turned off. And this is power bank turned off is that this thing is not consuming many load. This is not consuming load. That's why the power bank is thinking that I'm joking with it. So it just have to sleep. So now I'll show you that a LED floats in just one direction. You just have to show you that the thing, you just have to do this. Let me swap it. And then assume I'm just a novice. I don't know how to plug this thing, right? So I'll just plug it the wrong way. So now I'll plug it the wrong way. After plugging the wrong way, I'll show you again how I plug the wrong way. This leg, the LED wrongly. So with that, the light is not turning on no matter how I try. So I've done diagram 2 already. I've done diagram 3 already. This place I'm connecting the lights wrongly. even though I add the resistor there. So the light is not what? Light is not turning on. So let me connect it back properly. I connect it back properly and the light is what? Is turning on. So now the place I want to show you is the diagram one, where I'm going to put the resistor in the negative place. So now let us do that together. So let me just stop a second. I'll just replace. So I'll just replace here with here and here with here. So now let me try this time around. I've done a reverse of it. So let's go to open. This time I'm doing circuit diagram one, when I'm connecting my resistor to the negative of the light. So even though I did it the wrong way, it's still what? It's still turning on. I mean, even though I connected the resistor in negative, like what circuit diagram one is telling us about, it still was turning on. So now let's now do the experiment I said about, that this blue light is consuming a lot of light. So I'm coming. So let me disconnect it. Let me set stop. I'm coming. Now as you can see, we're having blue and red turning on. So let's see which of them is consuming more voltage. I mean, let's see the voltage each of them is consuming. So the power bank is turned off. So now let's look closely at the multimeter. For the red light, let's see how many volts it is using to work. Red light is using red light is using 1.92 volts, which was close to the 1.8 volt I said. So red light is using what? 1.92 volts to on. That means it's not consuming more voltage. Now let's see for this stubborn blue light. So let's see. The blue light, can you see now? The blue light is using what? So it has turned up. The blue light is using what? Using 2.7 volts. Wow. To turn on. But the red light is using what? Using 1.92 to turn on. So now if we to follow Kirchhoff voltage law, since this one is using 1.9, that means 5 volts minus 1.9. That means the resistor voltage should be close to the 3 volts. So let's see how many volts is on the resistor. The voltage on the resistor is uh, the voltage on the resistor is okay 1.92. I'm coming. See, the voltage of the resistor is what? 3.1 volt, as my calculation said. Now 3.1 plus the 1.9 the red light is using. So let's see how many volts the resistor this one is using. So this one is using what? 2.2 volts. Okay, 2.2 volts. How many is this blue light using? Blue light is using 2.7. So 2.2 plus 2.7. That is close to 4.9. I need to do something for this. Since this guy is using it. For me to make it stop offing, I just need to use another resistor to pull the power bank our current load. So this resistor added here is pulling more current. So the thing not going to turn off based on my theory. Huh? So now, as we can see, the red light is consuming 1.9 volts. Why this blue light is consuming what? Why this blue light is consuming what? 2 point something volt, close to what? Close to, oh, my fake snowball load did not work. Why this blue light is consuming close to like 2.6, 2.5 volt? That is tell you that Kirchhoff voltage law is what? Working very well in this one. Now, let us now see if late Mr. Ohm's law is working. From Ohm's law, Ohm's law is like if the resistance is very high, the current passing through is going to be what? Very low. So let's go to up. So this the resistor here is 330. Well, I've used it before, 330 ohms. 330. If I use 1 kilo ohms, this might not be the it's going to reduce also. Let me try it. This is this is my one. Sorry, I'm coming. Kilo ohms resistor. So that's what's going to happen. The light is going to still be bright a little bit, but we might be able to notice it. And also, the reason why they decided to increase the brightness of blue light, can you see it's blinking a little bit? That's because of the power bank is still dead. The power bank is dead. And listen, and the reason why the reason why they decided to increase the brightness of blue light is because of our eyes was not naturally evolved to blue light. As you can see, you might not be able to notice it here because of this camera will still fool us that is bright, but I'm seeing it, the thing has reduced. But a very good way for us to notice it is by us using 100,000 kilo ohms, and I have the resistor. So I have 100 kilo ohms resistor here. So this is it. These are my 100 kilo ohms. So let us see if it's truly 100 kilo ohms in our multimeter. So let's look at multimeter. Oh. So let's see what this guy is going to give us. It's giving us the resistance is very high, so you see the size is increasing. It's just changing, but the main resistance is 100 kilo ohms. And this is the second one here also. The second resistance, second resistor, which is 100 kilo ohms also. Let us forget what the meter is giving us. So now I'm going to substitute it. So we're going to be seeing it live. So let me connect for the other one. So now let's see, and let's plug it. 1, 2, ready, go. Okay, I'm coming. So let me join this. Can you see the light have already turned on now? At this time around, the power bank is not turned off. The power bank is still turned on. Okay, let me turn on the power bank. Can you see the power bank is turned on? I want to see the brightness of the light. This time alone, the camera can't fool us. Now this time around, the current going to the light is very low, causing the light to suffer. And the one suffering it most is what? Is the red light. Why? This is why the red light is suffering it most is. Let me just use some mathematical expression. This is why the red light is suffering it. Let me go to the board. See, we're having 5 volts minus the 2 volts. The resistor is carrying. Our resistor is taking 3 volts resistor. So now we're now having 3 divided by 100,000 kilo ohms. That should be close to 0.1, 2, 3, something like 0.0003 amps. This is for red light. Red light. Why for blue light? Blue light is 5 volts minus, let me calculate 3 volts. 2 volts. The resistor is what? 2 volts.
So the current for resistor is going to be 2 over what? 100,000. That's going to be around 0.0002 amps. Sure? I don't know, it might be more than 0. It might have more than 0. So now, come on, the thing is blue light. But the blue light is meant to suffer. But because of the blue light, as blue light uses more voltage than the red light, the blue light was able to still look at least a little bit brighter in our eyes than this what? Than this red light. So that's what is really causing the red light to look a little bit dimmer. Because of the voltage it is managing. Yet we are still doing a very smaller current to it. So that is the reason why the things are running very small. So this is it. Their resistance is very high. Let me change it to the one we were using before. Let's pity the blue light for now. So let's connect this and I connect this. You can see the thing increasingly became bastardly bright. So let's do it for the red light also. Let's pity the poor boys. I'll just use them for protocol. So now the thing already become what? Bright. But let's say that if you increase the resistance, it's like as if you are doing a lot of oversampling your circuit, and you yourself you regret it, because you might see that the power bank has turned off. You might see that your circuit is going to turn not work, whereas due to your high resistance that you are using. So that is the reason why that high voltage cannot damage those lights inside your socket. Because of this resistor there, you are seeing a resistor of 100,000 kilo ohms, 1 kilo ohms, and so it's difficult for the red lights for the socket and for the normal NEPA lights to damage it very fast because of the what? Resistor. So that is going to be all for today. So, and a little recap. We talk about resistors, talk about LED, talk about that they are a diode also, and a diode allows current flow in one direction. And as I did earlier, I swap the way I connected the LED and we also it. And I also said that blue light consumes more voltage, as I did with my multimeter. And I also did a demonstration of a resistor in series and a resistor in parallel, and also explained how this breadboard that has a lot of bunch of us work. So that was all for today, and the next class is going to be also what? Super great than this.